I only have one. But you definitely stole my category. I did.
All right. Any questions? Yes. What it means to buffer above or below? Okay, so what is going to happen? Let's see, we want period 2, add a page. Yep. So we're going to use just the most straightforward kind of buffer possible, which is the equimolar buffer, where you've got the same moles of acid as base. Yes? So let me just go here. So we have okay, so what we've got is we've got some weak acid, we've got its conjugate base, we have lots of this, and we have lots of this, yes? And for the purposes of today, we're going to say that HA concentration is the same as A minus, because even if they are different from one another, if we're making a buffer, they're going to be close to one another. They're not going to be like vastly different. Does that make sense? Okay. So for making life simple, we're going to make them equal to each other. And if that's the case, then Ka is equal to H3O. So what that means is more to the point, the concentration of hydrogen is going to be equal to the value of Ka. Yeah? And so the pH then of the buffer will be equal to pKa. So far, so good? Okay. And then what's going to happen is that as you add hydrogen, acid, what's going to happen is the equilibrium is going to shift left. Okay, so we add some hydrogen. Okay, there's our hydrogen. We just added some. This was our the hydrogen, and here at this point, this is the original buffer solution. So the concentration of hydrogen is equal to the value of Ka. Yes? And we increased concentration of hydronium or hydrogen, and so the concentration spikes. That's our stress. And then in our shifting process, as it shifts to the left, it's going to come back down, and it's going to get close to, but not quite to, its original value. Which means it's going to get close to the numerical value of K. Because hydrogen is equal to Ka. And that's all it means. So for example, if you had, I gave away my data booklet. I will find them. I need to tidy up in here. That's what I really need to do. Anyway, let's see. Let's pick an acid, shall we? Let's say we have benzoic acid. No, we don't want them. That one. Let's do hydrofluoric acid, HF. The Ka of HF is equal to 3.5 times 10 to the minus 4. That means the concentration of H plus in the buffer solution is 3.5 times 10 to the minus 4 molar. And if we want to, we can turn that into a pH value. So we can say pKa is equal to negative log of 3.5 times 10 to the negative 4. Calculator, what have I done with you? That's okay, I got another one somewhere. Okay. 3.5 E negative 4, and we log that, and we get 3.46. So, a buffer made with HF slash F minus will keep the pH relatively close to 3.46. Yeah? Now let's assume we were going to use let's use a different acid, just for funsies, okay? Let's use boric acid, H3BO3, okay? And we're gonna pair it with HBO3 minus. The Ka of H3BO3 is 7.3 times 10 to the negative 10. So the concentration of H plus in this buffer solution is 7.3 times 10 to the negative 10. And then our pKa is negative log of 7.3 times 10 to the negative 10, which is 7.3 E negative 10 equal log 9.14. So a buffer of boric acid and the hydrogen borate ion will buffer at a pH, it will keep the pH close to 9.14. And just this, I put this example in here just so you can see how woefully inaccurate the regular grade 12 explanation of buffers is. They're like, oh, if you have a weak acid and the salt of its conjugate base, it will buffer below pH 7. Well, this one is obviously buffering above pH 7. Okay, so actually, why don't you just put that out of your mind? Yes? And you can be like, okay, I know that I'm going to look at the Ka value, and that's going to tell me where it buffers. You have to pick the member of the pair that is the acid and look at its Ka value. Yes? Hey, why are you talking when she's talking? I cannot hear her at all. Hello. Yes. Oh, it should have been H2BO3. I'm so sorry. Dihydrogen borate. That was not on purpose. There we go. Anything else? Yes. Endpoint. Endpoint is essentially, it's almost the same thing as a transition point. Okay, the two can be used interchangeably. We just use them in different contexts, okay? So endpoint is used in the context of a titration. And it is the point at which the indicator changes color in a titration. Whereas the transition point is sort of a more generic term. It is the point at which the indicator changes color under any circumstances. It doesn't have to be during a titration. Okay, so we would tend to use the word transition point when we are doing things like calculating the Ka of an indicator. Yeah? We would tend to use the word endpoint when we are referring to a titration. But sometimes people will use the terms interchangeably. Like sometimes they'll say, what's the end point of this indicator, when they really probably should have said transition point? Yeah. Question? Yeah. So it's not that it doesn't, they don't, so they can kind of be used interchangeably. Is good? Okay. Yes. Question 6, and this is 109 of the workbook. Okay. Question 6, page 109. For each of the following titrations, specify the indicator from column 2 that should be used. Give a reason for your answer. All right, so what we've got is we have a strong base and a 109, number 6. We have a strong base and we have a weak acid. I know there's a K there, but that's okay, right? I mean, if you've got a strong base and this is a titration, that can't be a base, so it has to be an acid. Strong base, weak acid. Will that Will that equivalence point be greater than or less than 7? pH will be greater than 7. How about cesium hydroxide? What is that? That is a strong base. And HClO4 is a strong acid, so that will change at pH equal to 7. And then finally, we have a strong acid, and that must mean that this part here is acting as a weak base. The K is just a spectator, yeah? And so this is going, the equivalence point of this will be at pH less than 7. What? PE? Equivalence point. All right, and so let's pick our indicator. If we want the pH to be equal to 7, which of those 3 indicators would go with that one? Neutral red. Okay, and we want pH greater than 7. Orthocresol phthalate. Yes. And pH less than 7, we have bromcresol green. Now, if we need to explain that, the explanation for A is that OH minus, well, I guess we could write the whole thing. Can we write the net ionic equation? Are we all right with that? Yeah? Okay. If it freaks you out, let me know. We have OH minus plus, and then we're ignoring the K because it's a spectator. We have HC8, H4, O4, and that's negative. Now, the OH is going to do what? It's going to accept a proton. So we will end up with water and C8, H4, O4, negative. Yes? Huh? 2 minus, yes. Yes, yes. Now, why is this solution, because this is all we have left, this is all gone, right? At the equivalence point. Because that goes to completion. Because hydroxide is a strong base. Okay, because hydroxide will rip all the hydrogens off of, yeah, okay. And so all we're left with is water and C8H4O4 2 minus. Which of those things is making the pH greater than 7? This guy here makes the pH greater than 7. How does it do that? By hydrolyzing. Okay, so at the equivalence point, if there's ever a pH different than 7, it's always because of hydrolysis. So it does it by hydrolyzing and producing OH minus. So we could write that equation if we wanted to. C8H4O4 2 minus plus water. Now, is this a one-way arrow or a two-way arrow? This is a two-way arrow. And we end up with H, C8H4O4 minus plus OH minus. Yes? Do we want to do the explanations for the other ones? No, we're good? Okay. So basically, yeah, the second one would just not have any hydrolysis, and then the third one would have, would produce hydronium when the ion hydrolyzes. Okie dokie. Any other questions? Yes?
But HA on the version, what does it mean by acetonic hydroxide?
Okay, let's take a look. That's number 8 in the written. Okay, I do not love this question. So let's just cross it out. Okay, there we go. And I'm going to fix by omitting this. Should have done it years ago. Yes?
Can you go on to like page 72?
72?
Maybe go through the half equivalence point and the equivalence point of it, like maybe the half.
Okay. Okay. So just so you're aware, very little time on your test will be spent on any of the calculations around this. Okay. I've shown them to you because otherwise it's just like magic. Do you know what I mean? It's like, ooh, magic. I don't know why it's like this. Magic. It's because of magic. Pardon me? I can't hear you. I know there will be calculations as well, but if you remember, like if you're doing a calculation at the half equivalence point, it's basically the same calculation as for a buffer that we just talked about this morning, right? Because we have Ka is equal to A minus times HA. Yes? And what has happened is at the half equivalence point, let's go back here somewhere. At the half equivalence point, which is what? This one. Here we go. We started with 4 moles of the acid, and we neutralized half of it. Yes? Okay. When we neutralize half of it stays as weak acid because it has not been neutralized. What happens to the other half? It turns into the conjugate base. So at the half equivalence point, HA and A minus concentrations are equal. Is that just like a buffer? Yeah. Did you understand the buffer? That's it. That's all there is to it. Yes? And then at the equivalence point, oops. At the equivalence point, where was it? This is the equivalence point. So you have, at the equivalence point, you have OH minus plus HA, and you started with, let's say you started with 4 moles of this. At the equivalence point, you will have added how many moles of OH? 4 moles, which means that these are both going to go down by 4 moles, which leaves you with 0. And that means that this is going to go up by 4 moles. So all you have now is the base form. So initially, if we're doing a strong base, weak acid titration, initially it's all HA. Yeah. At the half equivalence point, you're going to have half is HA and half is A minus. And at the equivalence point, it's all A minus. Did that make sense?
That half of the first point of the half after was added.
There'll be half and half because you'll have, instead of having reacted 4 moles, you will have reacted 2 moles. Yeah?
At equivalence point.
That's at the half equivalence point now.
And then
At the equivalence point,
you use up all.
you use up all of the acid. Yes.
Why is that only 2 moles?
Why is it 2 moles at the start? For the half equivalence point, at the half equivalence point, I need to have reacted half of this. So I made the number here 2 because it is half of 4. Right? Because they react 1 to 1. So if I put 4 moles, I'd be reacting all of it, which would take me to the equivalence point. So if I want to react half of it, I only want to add 2 moles. Yeah? If I wanted to go all the way, then I would say, that'll take me to the equivalence point. Yeah? Yeah. Yes? Yep. You mean here? At the half equivalence point? Yeah. Yeah, divide by the volume of the mixture, yes. No. You're confusing. So there's 2 uses for a titration. One is go to the equivalence point. Don't worry about the pH. Go to the equivalence point. The indicator will tell you when you're done. All you're finding is moles. Okay? That was like on the practice quiz. You know, you had that question where you're just finding moles, and that's where you say, I wanted to know how many moles there were and what volume were those moles in. Those moles were in my original volume. Okay? But if I'm looking at pH, I've got my pH meter sitting in the mixture the whole time. Right? So anytime I'm looking at the pH through a titration, like separate sort of a thing, I am looking at the entire volume. Yeah? Yeah. That was a good question. It really gets at one of the things that's very confusing about this unit. Yeah. Yes? Yes. And in fact, if you got one yesterday, or the day before, you got some answers that were wrong. Yay! So awesome. So sorry. Okay, and I need to figure out where I'm going to put the things. There they are. So I will give everybody a new answer key to the practice quiz so that you don't have like the wrong answer for the last question in your head. I'm just going to open these for you. Okay. Go. Oh. They are so much. I don't know what's happening. Why is it the same on both sides? What's happening? I don't understand. Oh. That's okay. Oh. This is the answer key to both versions of the practice quiz. Oh. So, yeah. Go with the one on the front. Okay, go with the one on the front. Okay. Cross out the one on the back so you don't get confused.
Can you pass the same card and
Cross out the one on the back so you don't get confused.
Thank you. Oh wait, Miss Spence, we didn't get an answer.
For all.
So sorry.
And while we're at it, you guys are going to go
Where's the next
over
one?
here. And on the right-hand side, there is an NP acid base to review. So help yourself review that.
Review.
Far right. Unit, you're on the far right.
I know, I got it. Oh, thanks.
Second one. No, there's.
You already have one, you don't need to get another one.
Third one.
I got it.
Ready? Okay, one of them.
Yes.
Okay.
Anyway,
I don't. I've been trying to sit back.
Okay, we are going to take a look at number 105 and 106 on the review. So we have a titration here, which is being used for questions 102 to 105. And we are asked, first of all, what kind of a titration is this? What's in the flask? An acid. What kind of an acid? A weak acid. And what's being dripped into it? A base. What kind of a base? Strong base. We would never do a weak titration because that's useless. Yes? Okay. Now, 105. The salt produced by neutralization reaction here must undergo, and we're being asked what type of hydrolysis. So we can see that at the equivalence point, the pH is greater than 7. So whatever salt we got must be undergoing basic hydrolysis. Okie dokie? Yeah. So that's 105. And then for 106, I'm going to get rid of this because we did talk about this in the past, but we're going to talk about it from an AP framework. Yes? Because I've got a base and I've got an acid. Yes? And what I'm going to do is I'm going to look up my Ka for this acid. Ka for CH3COOH is 1.8 times 10 to the minus 5. Over here, I have NH3 and NH4. Who is the acid and who is the base? NH4 is the acid, and its Ka is 5.6 times 10 to the negative 10. Here, we have an acid, and here's our base. So the Ka for this acid is 6.2 times 10 to the negative 8. And then finally, I have a strong base here, which messes up everything and doesn't allow it to be a buffer. I mean, you could have a strong base, but it would have to go with a weak acid, and you would have to like get them to the half equivalence point. But what you've got is you've got a strong base and you have a weak base, and that is not a buffer. So we can eliminate that one immediately. Are we okay with eliminating that one? Okay. Now, what do you remember about buffers and the concentration of hydrogen ion in the buffer? Assuming it's equimolar. H plus equals Ka for a buffer. Because they have the same moles. Now, if we changed it to 0.8 and 1, it would be a little bit different, but not that much different. It'll be a little bit different, but it'll be close. Okay, so it really doesn't matter that they're exactly equimolar. If we're just doing ballpark, we're like, this one, our hydrogen ion concentration is going to be close to 6.2 times 10 to the minus 8, even if these concentrations are slightly different from each other. But it'll be close to that. This one, there's our concentration of hydrogen ion. In which of these situations do we have a basic hydrogen ion concentration? Which one is the closest to basic? B. Yes? Because if hydrogen is 10 to the negative 10, then what would our pH be? 10-ish, approximately 10. So that buffer will sit at pH 10, and it will keep the pH close to 10. No? Sorry? It means it keeps maybe it's the wording of the question that's messing you around, but it just means which of them would be the best at keeping the pH basic. Yeah? I think it might be the wording of the question that's messing you up. Yeah. Other questions? Yes? 9 and 10 from the AP review. Yes. I have to just do a quick print of that. Let's see. What? Oh my God. Okay. Here we go. You want a number 9, was it? 9 and 10? Perfect. Okay, so here is 9. Okay. We haven't covered this yet. Shall we do it right now? Let's do it right now. This is in the white workbook. So let's go to the white workbook.
We're doing white work.
White workbook. And we're going to go to 5.8G, which is on page 42.
Great. Anyone else who's way yesterday? Yeah.
Wait, that's the last thing.
Page 42, yeah. And it looks home fast.
Okay, so what we've got here is we have a triprotic acid, yes? Yes? Triprotic acid. And it dissociates, this is the first ionization. This is our second ionization. What page are we on again? We are on page 42. Answer to life, the universe, and everything. Second ionization. And then we have our third ionization. Now, if we were to combine these three, yes? The K value for the overall reaction, do you remember how we deal with the individual Ks to get an overall K? When we add them up, what? Huh? Okay. Do we remember? I think you remember. We multiply them. So when we add up reactions, we can multiply their K values to get the overall K. Is good? Okay. So that's it. So when you add reactions, to get an overall reactions, you multiply the K values to get the overall K. And while we're here, we might as well talk about the titration curve for a polyprotic acid. And so the titration curve for a polyprotic acid basically looks like a regular one, except that instead of having one equivalence point, you have two equivalence points. This would be a diprotic acid. Okay, so what's happening is during this little first section, we are reacting the first hydrogen because the first hydrogen comes off the most easily, yes? So the second hydrogens won't come off until all of the first hydrogens are gone, okay? So right here, that is our first equivalence point. And you could find Ka of the diprotic acid at the half equivalence point. Yes? Yes? Then we are reacting the second proton. And we hit a second equivalence point in the midpoint of our second vertical section.
Wait, however many ions, however many.
Yes. So if it were triprotic, it would go and a 1, and a 2, and a 3. Okay? This one just goes and a 1, and a 2. Yes? And then at the end, we just have excess NaOH, right? That causes the pH there. And we could, at our half equivalence point here, this pH equals pKa2. So that would be like the second hydrogen ion coming off. This is at the second half equivalence point. How often is this going to come up? Not very. You know, but, oh, look, there's 2 bumps, not just 1 bump. It must be diprotic. Yes? And I guess part of it's just realizing that all of the first hydrogen comes off, you hit an equivalence point, and then all of the second hydrogen comes off. Okay, and that's it. So here is our first neutralization. We have the NaOH plus H2CO3 gives NaHCO3 plus H2O. And then we're going to have our second neutralization, where we get a second NaOH plus, and now we're going to have the HCO3, and that's then going to become CO3 plus H2O. But this Na is also there, so this Na is going to become part of this Na here. So I guess I should say NaHCO3. HCO3. No, don't fuss. Just, yeah. There we go. Okay, the 2 here came from the fact that we have both this Na and this Na making those 2 Nas. Okay, you're not going to have to write this, All right, you're just realizing that one of the hydrogens gets ripped off, and then the second hydrogen gets ripped off. You're not going to have to write this, okay? Oh, look, we have the half equivalence point here, which we already talked about, right? Yeah. And here's our Henderson-Hasselbalch equation. Why are we using the Henderson-Hasselbalch equation here? Because we have a buffer at the half equivalence point. None of this is on the test on Monday because this is AP Extras. Okay? Now, when you're at the actual half equivalence point, not when you're right before it, not when you're right after it, but when you're exactly at the half equivalence point, A minus and HA are the same, and the log of 1 is 0. So this term becomes 0. So pH is equal to pKa at the half equivalence point. Yes?
Always.
And that's it for polyprotic acids. Done. All right, let's go back here and see if I actually answered that question. Where did it go? Hey. Oh, here we go. Okay. So for number 9 on that AP review, we have phosphoric acid, and in this case, how many hydrogens have come off? 2 of them. So are we looking at all 3 ionizations? No, we're just looking at the first 2. So it's going to be Ka1 times Ka2. Yeah? Because when you add those 2 together, you'll get that. Okay? All right. And number 10, calculate the concentration of hydroxide in a base with 0.1 molar and a Kb equals 1 times 10 to the negative 10. Now, I'm guessing that because this is a multiple choice question, we don't really want to do a whole Rice and Kb kind of thing because that would take a long time, yes? So what I'm going to do, just right in the inbox, please. Thank you. And you can put the pink thing there as well. What I would do is I would write my Kb expression. I've got B plus H2O in equilibrium with Hb plus OH minus, yes? And so my Kb expression would be Hb times OH over B. So far, so good? Okay. Now, I am skipping the rice table. If you feel uncomfortable with me skipping the rice table because you're like, how did you get that? Let me know. But what I'm going to do is I'm going to skip the rice table, and I'm going to say that these 2 guys are equal to x. Okay, so that gives me x squared. And B, on a multiple choice section, hell yeah. Not on written. On written, you write everything out, okay? So, concentration of the base is 0.01. Is it really 0.01 minus x? Yes, but what are we going to do with that minus x? We're going to assume it's insignificant. So if you're doing multiple choice, I actually, if you're really good at it, you wouldn't even have to write this part, right? You could just go straight to here, 1 times 10 to the negative 10 is equal to x squared over 0.01. And so x squared would equal 1 times 10 to the negative 12, which means that x is 1 times 10 to the negative 6. And that's our answer is B. So that's how you would deal with a multiple choice question like that, okay? You're just kind of skipping all the fun stuff. Super fun. Yes, Jade. Yep, number 12. Okay, which of the following equilibria lie heavily to the right-hand side? So we want to favor the product. So we want the stronger acid to be on the reactant side. Okay, so on the left. Oh, look! That looks like a good start there. That's a strong one. Do we have anything else that's strong on the left? Ooh, we got that. This should be NH2 minus. I need to fix that. So this is strong, this is strong, this is, strong. So that's no good. So it's not this one anymore because it's got strong pushing back as well, okay? And so it's going to be C because this is weak, weak, and water is like ultra weak, uber weak. Yes? Anything else? Yes?
For polyprotic acids.
Yes. Yep.
Why the ionizations take place in like B succession instead of like.
Okay, because the hydrogens, the first hydrogen is the most loosely held hydrogen. So if a base has a choice of reacting with a first hydrogen on one molecule or a second hydrogen on a different molecule, chances are it's going to react with the first hydrogen on this molecule over here, right? It's like that first hydrogen, they're giving them out like, woo, woo. The second hydrogen, they're kind of like holding it a little tighter. Okay, so it's harder to take it away. So not that that won't happen, you know, just occasionally, but there will be more of an equilibrium kind of effect there. So did that make sense?
Yeah.
Yeah, okay. Yeah. Yeah. Anything else? Yes? 22 and 25, yes, indeed. So here is 22 on the AP review. A buffer is to be made that has a pH of 11. And, sorry? 21. Okay. When considering the titration of HCN, a weak acid, with NaOH, a strong base, which of the following statements is true? Is the pH at the equivalence point below 7? Everybody should be able to say no. Okay. The salt at the equivalence point hydrolyzes according to the equation Cn minus plus water gives HCN plus OH. Is that true? Because if you have your NaOH plus your HCN, what do you get? H2O plus NaCN, and who's going to hydrolyze? Cn minus, and does it hydrolyze like this? Yes, so that's okay. Number 2 is okay. And would a suitable indicator be methyl orange? Methyl orange changes pH 3.2 to 4.4. That's our transition. Is that a good choice? Why not? Because this one is going to have its equivalence point above 7. You would want something that changes color above pH 7. Sorry? Because it's basic, because of this OH here.
Right.
Yes. Okay, so that's going to be just number 2 only. So number 21, and was there another one as well? 25. Which of the following indicators is most suitable for the titration of sodium hydroxide and acetic acid? So that is a strong base and a weak acid. So the pH at the equivalence point is going to be greater than 7. So which ones can we eliminate immediately? C, D, and E. And 7.9 doesn't really look much bigger than 7, does it? It's just a little tiny bit bigger than 7, so I'm going to go with that one there. If I wanted to figure out exactly what it would be, I would go with the Kb of CH3COO minus, which is CH3COOH times OH minus over CH3COO minus, because that's what we have, right? At equivalence point, we've got the acetate ion. And once again, that's going to be X squared over whatever that concentration is. But we don't have enough to do that, so we're going to have to just ballpark it, yes? We don't have enough to do any actual calculations, so yeah, just go with this one. There you go. 7.9 just seems too low. It's not that much bigger than 7. It's really close to 7. Yes? Yeah. And we want it to be greater than 7. What's causing it to be greater than 7? The hydrolysis of that acetate ion, because that's what you're going to end up with as your product. Other questions? Okay. Well, your homework, if you have time for it tonight, if you're not going to band,
No.
Is actually in here.
So
I know you're gonna love it.
That's why.
You're gonna come get this book, this yellow book, and the answer key. And you're going to do 6.1A with Tyler. It is a 13-minute video. It's only 15 minutes. If you have band, do it at lunch. Okay?
including the script.
Okay.
From actually. Yeah. And also accountable. Keep on doing it. I told them to do it this week. So hopefully by the time tomorrow,
6.1a.
do you think we're gonna have time after that? I don't know.
It's 15 minutes.
Do you think?
And you know what?
We'll have time.
If you don't have time, you can do it tomorrow. Do you know what I mean? Like it can fit in. It could happen on the weekend,
Yes.
right? It will be similar to this one.
So it can get 2
No.
This chat route said electrochemistry is like fun. Yeah, it's very sarcastic.
No, it is kind of fun. Like the balancing equations is fun. Because you're like, oh, I'm just balancing equations. Yeah.
Let's check. Nope. I know.
Let's find a pair of scissors. Scissors, scissors, scissors.
Yes.
You can ask first.
Yeah, you go first.
Mine is gonna take the.
Yeah, you go.